Hey everyone, today we're going to finish out that practice exam that we started on Tuesday. So we did the first 7 questions, so I'm just diving in right where we left off. For number 8, we want to find the derivatives of the following functions and don't simplify. Here we have a quotient rule problem. So we're going to break out our old friend Bodito minus Todibo over Bobo. The bottom is e to the x plus e to the minus x. The top is e to the x minus e to the minus x. So then the derivative of the bottom is, when we're trying to solve the derivative of e to the exponent things, we copy and paste e to the exponent and then multiply by the derivative of the exponent. So this first term is just e to the x, and if we multiply by the derivative of the exponent, the derivative of x is just 1. Plus, and then we copy and paste e to the minus x, and we multiply by the derivative of this exponent, which is minus 1. And then the derivative of the top, we're going to have e to the x minus e to the minus x times minus 1. We can go ahead and rewrite this a bit. This minus 1 and this plus work out to just be a minus e to the x. And this minus 1 and this minus work out to be e to the x plus e to the minus x. So if we throw this all together into our quotient rule, we're going to have the bottom times the derivative of the top minus the top times the derivative of the bottom all over the bottom squared. So that's the derivative of this part. And now for b, as always, it's helpful to rewrite everything in terms of exponents if we can. So we can rewrite this to be the natural log of 5x cubed minus 3x, that whole thing to the 1/3 power. And so here we can apply our chain rule, because we have a function raised to a power, so its derivative will be 1/3 times the natural log of 5x cubed minus 3x to the minus 2/3 power. And now all we have to do is multiply by the derivative of the inside. The derivative of the inside being natural log, or the inside being natural log 5x cubed minus 3x. When we take the derivative of a natural log function, what we do is we put 1 over whatever's in parentheses, and then we multiply by the derivative, by the derivative of whatever's in parentheses. So here we're going to have 15x squared minus 3. And because we don't have to simplify, we're done. That's our derivative of that. For number 9, we have 2 integrals that we want to evaluate. And just like when we're taking derivatives, it's helpful to rewrite everything as exponents. When we're taking integrals, it's also helpful. So this integral, we can rewrite it as the integral of minus 8 times x to the minus 3 over 4 plus x to the 7 plus 5/3 x to the 4 over 7 minus 5x to the minus 1 dx. And now we can just go term by term, adding 1 to the exponent and multiplying by the reciprocal. So this first term, we're going to have minus 8x to the, and we add 1 to the exponent, so minus 3/4 plus 1 becomes 1/4, and we multiply by the reciprocal. The reciprocal of 1/4 is 4, so we have 4 times minus 8 times x to the 1/4, plus, and then our next term, we add 1 to the exponent and multiply by the reciprocal, so we get 1/8 x to the 8th, plus, here we're going to have 5/3 x to the, and if we add 1 to the exponent here, we're going to have 11 over 7, and we multiply by the reciprocal. And the reciprocal of 11 over 7 is 7 over 11, minus, and now we add 1 to the exponent and divide, but here we get a divide by 0 error. And if we're ever taking an integral and we get a divide by 0 error, it means we need to have a natural log there. And so this, we get 5 times the natural log of x. Plus c. Always have to throw on your constant of integration. And now if you want to, you can go through, if you're nervous you did an integral wrong, you can always take the derivative of your answer. And if we were to go term by term taking a derivative, we would end up, this term would become minus 8x to the minus 3/4. This term would become x to the 7th. This term becomes 5/3 x to the 4/7. And this term becomes minus 5 over x. So we did that one correctly. For b here, we already have everything in terms of exponents, so that's really nice. It might be helpful to break this apart into different integrals. So let's go ahead and do that. We have the integral from minus 1 to 1 of e to the x minus the integral from minus 1 to 1 of e to the minus x. And the reason I'm doing this is because if we're ever taking the integral of e to something that isn't x by itself, we have to use u substitution. Okay? But the issue is, if we use u substitution without breaking apart first, then this exponent would become e to something that isn't u by itself, so we'd have to use some other u substitution. We'd keep going back and forth. So it's helpful to just break this apart into two different integrals. This integral is easy to take, right? It's just e to the x, and we evaluate from minus 1 to 1. This integral, we have to use u substitution. So we're going to let u equal minus x, then du dx equals minus 1. So then dx equals minus 1 times du. So this becomes the integral as x goes from minus 1 to 1 of e to the u times minus 1 du, which is minus e to the u, evaluated as x goes from minus 1 to 1. And so let's write that over here. So we have minus e to the u, evaluated as x goes from minus 1 to 1. But of course, u is minus x. And now we can solve this. Let's evaluate this term. We're going to get e to the 1 minus e to the minus 1 minus, now plugging in our endpoints over here, we're going to have minus e to the minus 1 minus e to the minus 1. Okay, which is a little complicated. Let's simplify this down a bit. This becomes plus e to the 1. Simplifying this all out, i.e. distributing this negative here, this becomes e to the 1 minus e to the minus 1 plus e to the minus 1 minus e to the 1. So those cancel, we get 0. Number 10, more integrals. This time, they're complicated looking integrals, so we're probably going to need to use u substitution. All right, let's take a look at this guy. Is there any part of the function whose derivative appears elsewhere? Yeah, and even if you're having trouble finding a part of the function whose derivative appears elsewhere, a natural kind of guess for the u is the part with an exponent in it, if you're dealing only with polynomials. So here, the natural thing is, since this has an exponent with it, let's let u equal 2x to the 4th plus 6x, then du dx equals 8x cubed plus 6. So then dx equals du over 8x cubed plus 6. And what we can do is we can factor out a 2 here. And doing so, if we rewrite our integral, we have the integral of 4x cubed plus 3 times u to the 1/3 times du over 2 times 4x cubed plus 3. Now we get the cancellation that we know and love from u substitution. This becomes the integral of 1/2 u to the 1/3 du. And we can solve this by adding 1 to the exponent to get 4/3 and multiplying by the reciprocal. Plus c. And now we just need to trade our u back in for x's. So we get 3/8 times 2x to the 4th plus 6x to the 4/3 plus c. Okay, and for b, is there a part of the function whose derivative appears elsewhere? And this one is kind of subtle and tricky. But like we talked about earlier, if there's a part of the function that has a random exponent to it, we should probably let that be the u. So let's let u equal the natural log of x. Then du dx is 1 over x. So then dx equals x times du. So now we have the integral as x goes from 2 to 4 of 4 over x times u squared times x du. We get the cancellation that we know and love. This is the integral as x goes from 2 to 4 of 4 times u to the minus 2 du. We add 1 to the exponent, we get u to the minus 1. And if we divide by this larger exponent, we get a minus 4 u to the minus 1, evaluated as x goes from 2 to 4. Now we just need to trade our u back in for x's. This is minus 4 times 1 over the natural log of x, evaluated as x goes from 2 to 4. So this gets us minus 4 over natural log of 4 minus 4 over natural log of 2. And ta-da! Okay, and I may have gone over this quickly. The reason we get 1 over natural log x is because we plug in natural log x here. We have natural log x to the minus 1, so that means we flip it to the bottom. All right, number 11. A company purchases a new machine for which the rate of depreciation can be modeled by this thing. dv dt equals 10,000 times t minus 6, where t is between 0 and 5. Where v is the value of the machine after t years. What we want to do is set up and evaluate the definite integral that yields the total loss of the value of the machine over the first 2 years. So to determine the total loss of the value of the machine over the first 2 years, we need to know the value at 0 years and the value at 2 years. And to determine the total loss, our goal is to find v2 minus v of 0. Okay. Now, I don't know about you, but this kind of looks like the integral from 0 to 2 of dv dt. Right? And the reason why is because if we take the antiderivative of this, remember this is the derivative of our value with respect to time. If we take the antiderivative, it'll tell us our value function. And once we have our value function, we can plug in 2, we can plug in 0, and we can find the difference between the two. So ultimately our goal is to find the integral from 0 to 2 of 10,000 t minus 60,000. Right, I've just distributed the 10,000 in there, and this is with respect to t. The antiderivative will give us 10,000 t squared over 2 minus 60,000 t evaluated from 0 to 2. So if we plug in 2, we're going to get 5,000 times 2 squared minus 60,000 times 2 minus And if we plug in zeros here and here, we're going to get a big fat 0, big goose egg. So this is 20,000 minus 60,000 equals minus 40,000. So that tells us so the machine lost $40,000 in value. All right. Number 12, find the consumer and producer surpluses by using the demand and supply functions where P is the price and X is the number of units. So consumer and producer surpluses, these are just kind of equations we need to memorize. Consumer surplus is the integral from 0 to X naught of P naught minus supply. And producer surplus is the integral from 0 to X naught of demand minus P naught. So step 1 is we need to find X naught and P naught. And the way we do that is we set the functions equal to each other. Because X naught and P naught, that's the point of equilibrium. It's where supply equals demand. So we set the supply and demand function equal to each other. And we solve. Okay. So if we subtract 100 from both sides, we get 300. And if we add 0.4x to both sides, we get 2x. So 300 equals 2x, so x equals 150. So then our price, P, is 400 minus 0.4 times 150, which is, I think, 60. Let me pull up a calculator. Yeah, 60. So then this is 400 minus 60 equals 340. So our X naught is 150. Our P naught is 340. So now we can find our consumer surplus is the integral from 0 to 150 of 340 minus 100 plus 1.6x. This is 240 minus, and then I don't know what 340 times 1.6 is. Oh, I don't even need to do that, sorry. Sorry, we're not distributing a 340, we're just distributing a negative. So we're here. We can take the antiderivative. We get 240x minus 1.6 over 2x squared, evaluated from 0 to 150. And now we just plug into our calculator. And I'll leave that part to you. To find our producer surplus is the integral from 0 to 150 of our demand function, 400 minus 0.4x, minus our P naught of 340. So this is the integral from 0 to 150 of 60 minus 0.4x dx. If we take the integral, we'll get 60x minus 0.4 over 2x squared, evaluated from 0 to 150. And again, now we just plug into a calculator. I'll leave that to you. Producer and consumer surplus. One last question for us to worry about. A company manufactures running shoes and basketball shoes. The total revenue from X units of running shoes and Y units of basketball shoes is given by the following function. R equals minus 5x squared minus 8y squared minus 2xy plus 42x plus 102y, where x and y are in thousands of units. Find x and y so as to maximize the revenue. So our goal here, we have this multivariable function. Our goal is to find the maximum of a multivariable function. In order to do that, we need to find the first partial derivatives. So Rx is minus 10x minus 2y plus 42. And Ry is minus 16y minus 2x plus 102. We find the two partial derivatives. We're going to set them equal to 0. And now we can try and do some substitution. Let's look at this top line here. This top line can be rewritten as minus 2y equals 10x minus 42. So then y equals minus 5x plus 21, just dividing through by minus 2. Let's plug that into this second equation. We have minus 16 times y, but instead of y, we'll write minus 5x plus 21 minus 2x plus 102 equals 0. 16 times 5 is 80, I think. Perfect. So 16 times 5 is 80. So this gets rewritten to be 80x. 16 times 21 is 336. Carrying out the negative, we get minus 3. I forget the number I just said. 336? 336. All right. Minus 336 minus 2x plus 102 equals 0. So this gives us 78x minus, I should just keep this calculator up, 102 minus 336 gives us minus 234. So that gives us that 78x equals 234. So then x equals 234 divided by 78. Oh, I messed up. 234 divided by 78 equals 3. So we find that x equals 3. And so from there, we can plug x equals 3 into this to get y equals minus 5 times 3 plus 21. That's minus 15 plus 21. So then y equals 7. And we're done. I guess technically we could determine that these are maximums and minimums. Like, we don't technically know that x equals 3, y equals 7 gives us a maximum. Maybe it gives us a minimum. How do we determine if something is a maximum or a minimum? We have to plug it into this d thing. d of xy is fxx of xy times fyy of xy minus fxy of xy times fyx of xy. So we have this thing here. Let's find our second partials. Ignore this. I'm going to continue down here. So our second partials, rxx, that's the derivative of this thing with respect to x, is minus 10. Rxy, that's the partial derivative of r sub x with respect to y, gives us minus 2. Ryx, we don't even have to actually calculate it. We already know this. So if rxy equals minus 2, then ryx equals minus 2. The order of differentiation doesn't matter. And lastly, ryy, that's the derivative of this thing with respect to y. That's going to give us minus 16. So then we can plug this all together. D is minus 10 times minus 16 minus minus 2 times minus 2. This is going to be 160 minus 4, which is 134. So here we have d is bigger than 0, and rxx is less than 0. So x equals 3, y equals 7 is a maximum. And we're done. And we're ignoring problem 14 because it has to do with Lagrange multipliers, which we didn't cover this semester. Thank you very much.